In this video, we're going to cover section 1.3.3 on experimental methods. So the question we ask is, how does one experimentally determine the rate of a reaction? Well, the essential feature of all experimental methods for studying the kinetics of a reaction is to determine the time dependence of the concentrations of reactants or products. And when we choose a method for kinetic measurements, it depends on two things. It first depends on the species involved, and secondly, the time scale over which the reaction occurs. With respect to the species involved, it's important that we choose an experimental method which allows us to easily detect that change in concentration for a particular reactant or product. And with respect to time scale, we want to ensure that the experimental method we choose can follow that change in concentration in real time. And so if the reaction proceeds in a very short time scale, then we need to choose an experimental method that can capture or collect that information on that same time scale. Now, the experimental methods that are usually used to collect this information are often categorized into two groups: chemical and physical methods. With chemical methods, this relies on some sort of chemical processing to determine the progress of a reaction with respect to time. Generally, in this method, a chemical reaction is initiated, samples are removed from the reaction, and they're manipulated in such a way that the sample is quenched. Now, quenching the reaction can be accomplished by rapidly cooling the sample or adding some reagent that depletes one of the reactants. Once the reaction has been quenched, the solution can be examined by slow conventional techniques. These are often referred to as steady state techniques. And they may include various forms of spectroscopy, such as UV-Vis near-infrared, fluorescence spectroscopy, NMR spectroscopy, mass spectrometry, liquid chromatography, gas chromatography, and electron pair resonance spectroscopy. By performing this analysis on a series of samples removed from that original reaction vessel as a function of time after the initiation of the reaction, the kinetics of the reaction can be determined. Now, chemical methods are generally limited to reactions that occur on slow time scales. Physical methods, on the other hand, they rely on monitoring a physical or spectroscopic property of the system as the reaction proceeds. So these methods involve techniques that are capable of monitoring the concentration of an individual species as a function of time, such as absorption measurements can be performed, in which the concentration of the species is monitored using the electronic absorption of a molecule in the Beer-Lambert law. Similarly, fluorescence measurements can be performed in which the concentration of a species is monitored using the electronic emission of a molecule, quantum yields, and that same Beer-Lambert law. Vibrational spectroscopic measurements using infrared absorption and Raman scattering can be used to monitor vibrational transitions of reactants or products, providing information on their consumption and production. NMR and EPR spectroscopy are useful techniques for following reaction kinetics of complex systems as well. Now, the challenge in chemical kinetics is to perform measurements with sufficient time resolution to monitor the chemistry of interest. If the reaction is slow, seconds or longer, then chemical methods can be used to monitor the kinetics. However, many chemical reactions occur on timescales as short as picoseconds, 10 to the minus 12 seconds, and femtoseconds, 10 to the minus 15 seconds. Reactions occurring on these short timescales are most easily studied using physical methods, and we have here three methods which we'll discuss in some detail: stop flow techniques, pump probe spectroscopy, and perturbation relaxation techniques. A stop flow technique provides a convenient method to measure solution phase reactions that occur on millisecond timescales, so 10 to the minus 3 seconds. This technique involves two reactants held in separate syringes that are connected to a syringe pump, so the driving piston shown here. The reaction is initiated by depressing the reactant syringes, releasing the reactants into the connecting mixing chamber, where the solutions are mixed. And then the reaction is monitored by observing a change in absorbance or some other spectroscopic property of the reaction solution as a function of time. As the reaction progresses at a steady and continuous flow rate, it fills the stopping syringe. It will expand until it hits a block, thereby stopping the flow of the reaction. So the change in concentration of one or more reactants during the course of this reaction can be monitored from that initial mixing stage until the stopping syringe is filled. And it is the data collected during that time period that can be used to understand the chemical kinetics of that reaction. So again, stop flow techniques are very useful for measuring solution phase reactions that occur on millisecond timescales. Pump probe spectroscopy is used for reactions that are initiated by a pulse of light. Now, light pulses as short as 10 femtoseconds can be used to study reaction dynamics on the ultrafast timescale. This is the same timescale as vibrational molecular motion. So typically, ultrafast spectroscopy has been used to study the reaction kinetics of processes associated with vision, photosynthesis, atmospheric processes, and charge carrier dynamics in semiconductors. This is the typical setup for a pump probe spectroscopy experiment, in which a reactant is photoinitiated with a laser source. And then some short time later, we can monitor the absorbance of the photoinitiated species using a probe pulse. So the same laser is used to generate both the light source that initiates the reaction as well as the light source that monitors the reaction. And this is the pump probe process. So the same laser source is used to excite the sample, and a small fraction of that light is reflected off a beam splitter and sent through a longer path. And so we can vary that path length, which varies the time delay between the pulse that initiates the reaction and the pulse that monitors the reaction. And in this way, we build up a histogram, or we can watch how that concentration of that species changes over time. And as a result, we can monitor the kinetics of that photoexcited event. Now, a third experimental method that we can use for reactions that occur on fast timescales are known as perturbation relaxation techniques. In this approach, we take a chemical system initially at equilibrium and we perturb the system so that it's no longer at that equilibrium. And then we follow the relaxation of the system back towards a new equilibrium. And we can determine the rate constants during that relaxation process. Any system variable that affects the position of the equilibrium, such as pressure, pH, or temperature, can be used in a perturbation relaxation experiment. The most common experiment is the temperature jump experiment, and that's shown in this particular figure, where we have a system under equilibrium at one temperature, and then we quickly change the temperature of that system and follow the relaxation towards that new equilibrium. And so this temperature change could be induced through electrical discharge or a laser pulse, but you're dramatically changing the temperature of the chemical system such that it's going to relax to a new equilibrium. And it's the data collected during that relaxation process that we can use to determine the kinetics for this particular process. So if you have any questions about experimental methods that are used in chemical kinetics, by all means, send me an email. Thanks.